So today's session is a discussion led by Saleur about geometrical lattice models in 2 dimensions and how they give rise to conformal field theories.
Okay, thank you, Sylvain. Thank you for inviting me. Thank you, everybody, for coming. So I've prepared a rather informal discussion because it's really a huge topic and I didn't feel like being pedagogical. So it's mostly going to be a set of remarks, some of them, most of them for the initiated. As for the others, I'm sure they'll find some interesting material anyway. So I'll start with some sort of historical way of thinking of the problem, and then I'll discuss more advanced topics towards the end. So what do we mean by geometrical lattice models, first of all? Well, this is something that occurred naturally at the very beginning of CFT back in the late 80s, when people wanted to consider the natural definitions of the Q-state and ON Potts models, and a Q-state Potts model and ON model, of which we knew they were critical for some domain of parameters, that Q between 0 and 4, and N between -2 and 2. When people started asking themselves what the associated conformal field theories could be, and in fact, how to define these models. So the question of extending the definition of the models to N and Q real was in fact an old question in statistical mechanics. It can be tackled in various ways, and one way, the most natural way, is to use geometrical definitions. So by geometrical definitions, what we mean typically is that we perform some sort of high temperature expansion or low temperature expansion, depending on the point of view, for a model which is initially well defined, meaning it has N integer or Q integer. And then once you have this high temperature or low temperature expansion, Q or N appears as a simple parameter, and you can do an analytic continuation from Q and N integer to Q and N real, an idea that really goes back to Baxter. This is what we initially called geometrical lattice model. It is a geometrical definition, a geometrical extension, if you wish, of models which are initially defined only for integer values of the parameters. So typically this...
question.
Yeah.
So in your formula, it looks like N could even be complex because it is
yes,
N.
absolutely. That's why I allowed Q and N to be in C formally, although, as you know, nobody has ever worried about the definition of these models for Q and N complex. The problem being that critical manifolds, if Q or N are complex, seem to require, if you want criticality, you need to have complex couplings, hence complex Boltzmann weights, and that's usually something we try to avoid. If you keep Q and N real, then the Boltzmann weights are real, even though they may be negative, and even though the model may be slightly non-local. That's a point I'll get back to later. But yes, good point. We could take Q and N complex, and that's a topic that I think apart from you, Sylvain, very few people have explored. Well, maybe Slava and his collaborators also.
There are a few math results on the Gibbs measure being well defined that would require, for example, in the Potts model Q to be strictly larger than 1, I think, and real. But not even between 0 and 1. I'm not quite sure the math people would completely agree that the models are well defined in their sense.
I agree. It's really a slightly annoying question, but I'm sure we could go to Q and N complex. But I think the philosophy has been that Q and N real were already so difficult, there was no point exploring the complex case. But maybe that's a too narrow-minded way of thinking, and maybe thinking of the complex case would be very useful. Anyway, to carry on, these geometrical extensions, these geometrical definitions of lattice models, a priori are rather well defined, although they are in fact hiding a bunch of subtleties. So for instance, partition functions are well defined. I will get back to this a little bit later. And so are most correlation functions. A typical example of this is the ON model, the model which is probably the easiest to define in D equals 2. Again, we could do this in higher D, but I'm focusing on D equals 2, where, as you all know, the partition function of the model is simply defined by drawing on your favorite lattice, or in fact in a continuum, a loop gas where you have to draw self-avoiding, mutually avoiding loops whose fugacity is the parameter n, and for which there is an extra weight associated with the length of the loops, beta c to the number of edges. So the critical manifold is obtained when beta c is equal to some special value, beta critical of n, and it's well known that when n between is -2 and 2, there is a critical phase. In fact, there are two critical phases, the so-called dilute and dense, but that's a minor point here. So this model is known to be...
What are the edges here?
What are the what?
The edges, what do you call edges here?
Edges is simply the number of monomers. So you imagine drawing your loops on a lattice, for instance, say the honeycomb lattice. So you draw your loops on the honeycomb lattice, and then these are the edges, right? It's simply the number of elementary edges that belong to the loop. It's a fugacity per monomer. Now, of course, you also know that these models have special values of n where they take a special interest. In particular, in this case, n equals 0 is deeply related with the problem of self-avoiding walks. That's one of the reasons why people was interested in these models also. So the partition function is well defined in the plane. It's also well defined on the torus. On the torus, you draw the same loops and you demand that every loop, whatever its topology, gets the fugacity n. That defines a well-defined object statistically for which you can ask what the continuum limit is and so on and so forth. Similarly, a lot of correlators do have a geometrical interpretation. For instance, the spin-spin correlation function is a very simple object in the ON model. You simply have to draw, on top of all your self-avoiding and mutually avoiding loops, a line connecting I to J with the rule that this line is also self-avoiding and mutually avoiding. It's not totally clear that all the natural observables in the ON model for n integer have a nice geometrical interpretation. This is something that might require more discussion, but at this stage, I will not really get into it. It's, on the other hand, quite clear that if you take more complicated expressions in terms of the spins, you can build a whole set of correlators. And in particular, there are well-known correlators that we studied with Bertrand back in the old days, associated with the so-called watermelon operators that have also some simple meaning in the ON language. So you can play this game with the POTS model, you can play this game with the ON model. These are the two main models one can consider. There are more advanced variants, of course. The quantum Hall effect leads to some more complicated geometrical formulations. And then there are yet other models, like the so-called animals, dimers, you name it, a bunch of geometrical models that we can invent. And they're interesting for various reasons. And one of the main reasons I come to is that these models always involve some sort of non-local aspect. It's not necessarily obvious where the non-locality is, but you can see it if you think a little bit, for instance, about the ON model. You have this rule that every loop must get a fugacity n. And the question of whether you have one loop or several loops is a question that's typically a non-local question. If you have, for instance, a local configuration of two little pieces of loops like this, you do not know, if you look only locally, whether this configuration arises from two loops, like this, or whether it arises from only having one loop like this. Hence, the question of whether you should give a fugacity n square or n has an answer that requires some non-local information. So at the very beginning of the story, there was even the fear that maybe these models were not conformal invariant. And in fact, there exist some geometrical models that are not conformal invariant, even though they are scale invariant. The animals, for instance, are believed not to be conformal invariant, but they are the exception rather than the rule. One of the reasons why these models, in fact, are conformal invariant is that in many cases, it's easy to see that the non-locality can be traded for locality at the price of introducing complex Boltzmann waves. So this is something that's well known. I'm not going to explain it in much detail, but the idea is you can reproduce the weight n from loops by introducing some complex weights associated with left and right terms. And in this way, you can make the model into a local model. Local, but involving complex weights. However, the complex weights do not create too many problems. The Boltzmann weights in the end, the eigenvalues of the transfer matrix in the end are usually real. The exponents are real, and so on and so forth. So it's simply natural to expect that these models are described by conformal field theories, but non-unitary conformal field theories, something that's been known for a very long time. And you can see this non-unitarity in many ways. For instance, in the ON model at n equals 0, all the physics is contained in states whose norm square is equal to 0. And yet we want to study this state. So we have to invent other metrics that are not positive definite in order to give a meaning to the models. More recently, it's been something that was suspected for ages, but it's been established in a very solid way that all these models are in fact logarithmic, and I should cite here the nice work by Gorbenko and Zan. Scream if I'm forgetting some people. And then there's been work by Sylvain and Rongvoram, and work by Jesper, Linnea, and myself, establishing that these models are generically logarithmic and generically seem to involve Jordan cells of rank 2. I insist on generically because when we are non-generic, and what this means I'll explain later, then the logarithmic structure is considerably more complicated. All right, so some important remarks about these geometrical models. Whenever you reformulate a model geometrically, you realize that there are several possible ways to do such reformulations. There are different geometrical formulations which are possible. They usually give rise to the same partition function, and that, when you think of it, is a constraint, right? Because the way you start is by writing the partition function in some sort of geometrical way, and this is how you define your geometrical model. But nonetheless, these geometrical formulations may involve different sets of operators, different OPEs, and presumably different conformal field theories. This is a topic of confusion, whose simplest manifestation is probably what happens in the Potts model, where there are at least two naive formulations. One involves the cluster formulation, the natural so-called Fortuyn-Castellin formulation. And I'm sorry, I'm not reminding you of what this is. I kind of assume everybody knows. Where you formulate the Potts model partition function in terms of clusters. And then there are other formulations. For instance, one that is well known, that we have used a lot, of course, goes back to Baxter as usual, is the formulation using surrounding polygons, where you trade the clusters for a set of loops. The surrounding loops of the clusters, in particular involving an outer loop, which is often called the hull, and then inner loops. There are yet other formulations. For instance, there is a very natural formulation involving spin cluster. You can imagine expanding your partition function for the Potts model simply by drawing spin clusters, say Q equals 3. You're going to draw the cluster of spins equals 3, equals 2, equals 1. And then you can massage the statistics of the model so that you end up with a model defined for Q arbitrary. And that's a model defined in terms of spin clusters. And these formulations are not necessarily equivalent. They involve different set of observables. And one of the questions has always been, how are they related? Are there several CFTs? Should we think of only one big CFT containing everything? And so on and so forth. So this kind of question, I think, remains open. And it's one of the reasons why we like these supersymmetric formulations, at least for some values of Q and N, that they give rise to a completely unambiguous geometrical formulation. So the fact that the geometrical formulations involve different set of observables is, again, a source of confusion here. I wanted to explain it a little bit further. For instance, in the Potts model, we and others have studied different kinds of quantities, the simplest of which concerns the probability that 2 points belong either to the same cluster or to the same cluster boundary. In the first case, the probability that 2 points belong to the same cluster is illustrated on this diagram here. And that simply means we're asking ourselves what is the probability that two sites I and j belong to the same cluster. This corresponds to the Potts order parameter in the ordinary Potts model. This is the high temperature expansion of the Potts model correlation function. So we have devoted, and Sylvain and Raoul and others have devoted a lot of energy to studying the 4-point function of these operators. They are not the same as the probability that 2 points belong to the boundary of the cluster, which corresponds to the so-called Hull operator correlation function. The conformal weight is different, the spectra are different, the 4-point functions are different, and so on and so forth. And once again, whether there are several associated LCFTs containing these different sets of observables and how they are related is one of the questions that, to me at least, remains open. Am I okay? Are you? I'm not getting many questions, so I suppose everything is well known, but I'll carry on in this style anyway. So when you have this geometrical formulation, one of the natural things to ask is whether when Q or N is integer, your formulation recovers the genuine Q or N integer minimal model. And that's also a subtle question. Certainly at the level of the partition function, it's got to be true because we use the partition function to define an analytic continuation of the models. It's not necessarily true at the level of the correlation functions. Correlation functions outside of the minimal model can still be defined. For instance, even in the Ising model, even in Q equals 2, you can ask yourself what is the probability that two spins belong to the same Fortune-Castellin cluster, or you can ask what is the probability that 2 points belong to the same cluster of, say, up spins. These questions still exist even in Q equals 2, and they are described again by aspects of a conformal field theory that is bigger than the minimal model, and in some sense contains the minimal model. Once again, this is an aspect that we do not fully understand, although I think we are very close to understanding it. So, like I said earlier, all these geometrical models have an interest in their own right for special values of Q. In particular, Q equals 1, of course, is of great interest to mathematicians. So is N equals 0, self-avoiding works, and this is related with a lot of other stuff. Therefore, all the study of geometrical critical phenomena and the epsilon expansion that Bertrand and Jacques Descloiseaux worked on in the old days, and so on and so forth. Of course, also, once you've allowed yourself geometrical formulations, you can play with these models and change the rules of the game. For instance, if you have a loop model, you could decide to modify the rule. For instance, you could decide that the loops could be Brownian loops instead of self-avoiding loops. And you could decide that maybe Brownian loops are not allowed to overlap, or they're allowed to overlap in some way. This gives rise to a set of other models, some of which can be studied mathematically rigorously. In particular, the Brownian loop soup, I think, is something that hasn't been studied enough in the context of CFT, and that's one of the topics I would like to understand a little bit better myself. But this whole world of models is there, it's well defined, and it has, in some of its most complicated corners, well, the quantum Hall effect, statistics of the wave function for the quantum Hall effect at the integer plateau transition, that's one of the most complicated models. At the other extremity, one of the simplest models is probably spanning trees, C equals -2 symplectic fermions, and these two, in fact, may be related. All right, so that's enough for the models. I could also, by the way, mention, once we are there, that we could also add disorder, another fascinating possibility about which we know a little bit. That's definitely enough models to keep people busy for a lifetime. So now I come to the second part of the discussion. What do we know? Well, in a way, my feeling is now we know everything. Now it's solved, and I can retire or move on to other topics. Only we haven't managed to put it in order yet, but I feel the knowledge is there. All it's going to take is a couple of brilliant students, a couple of PhD theses, and that will be all out. It was a long story, however. Exponents, critical exponents, were determined very early on by using ideas of a mix of conformal field theory, Coulomb gas, and so on and so forth. And there's a bunch of names associated with this. Of course, there were the works of Dovzhenko-Fatayev, Dan Nice and Ninhuis. Then, of course, Bertrand and I did a lot of things, and then pretty much all the exponents were known by that time, early 90s. And the exponents, of course, at the time were very surprising because they involved conformal weights for which we had no idea how to calculate the 4-point functions. Typically, the exponents were involving using the caps labels, things like H1/2 0, for instance, that's the Potts model operator, Potts model order operator. And this was very confusing at the time because this field, of course, was non-degenerate. And when we were looking at the construction of the Dovzhenko and Fatayev, there seemed to be a claim that you could only build 4-point functions of operators that were degenerate. These were the only 4-point functions for which you could do the screening. If there was no screening, there was no 4-point function. It was a huge source of confusion for many years, and it took quite a while for this source of confusion to be at least partly dispelled. At the same time as the exponents, partition functions, remarkably, yeah.
So you were asking for, you wanted questions.
Yeah, sure, go ahead.
So of course there are still exponents which are not known. So for example,
yes.
the backbone exponent, shortest part exponent, and even for percolation, if you want, if you look at just at a point and ask how many surrounding paths can you get on the same cluster, that's something that was only discussed this year, and exact results are not known.
That's absolutely fair. That's absolutely fair. I think, however, the exponents which are associated with local observables in the ON or Potts model when n is q is integer, extended to n and q real, all these exponents I think are known. Yes. So the naive continuation of the field theories, I think, is for this things are roughly under control. But yes, there are always more geometrical exponents.
It always fascinated me, for example, when I think it was Bertrand Duplantier who first discussed this external perimeter.
Yeah.
When you make the shortcut of not going into the fjord, jumping one lattice step, you see that you get another exponent. But if you jump more than one lattice step, then it stabilizes. It's universal. So it's a bit like you cannot define any exponent that you want. I mean, you cannot keep inventing exponents, but there are still many which are not under control.
Yeah.
So the question is, what is the set of possible exponents that you can define? And I think that's a fascinating issue.
That's a fascinating issue, and surely the answer must be some sort of Russian doll structure where there are more and more CFTs containing more and more exponents, or maybe there are CFTs with some subsectors which are common and they are not fully included into each other. Yes, indeed, we don't know about this. I would say it's a wild problem, really, like wild in a technical sense. There's probably an infinity, non-classifiable infinity of CFTs, but maybe not. Anyway, for the simplest of all cases, partition functions, the continuum limit of this partition function on the torus, are also well known by some actually rather simple calculation we did back with Jean-Bernard and Philippe Di Francesco in the 90s, and then many other people worked on this also. It's not totally clear what these partition functions mean. That's another question that many of us have been concerned with, because when n and q are real or even complex, these partition functions, of course, can be expanded on characters of the Virasoro algebra, but the multiplicities typically are non-integers. They are functions of n and q. They turn out to be polynomials. And the meaning of these in terms of symmetries is something that's not totally clear. And there's been a lot of work in trying to define what ON and SQ might mean for n real or q real, and what this has to do with the multiplicities in the partition function. I guess Slava would have a little bit more to say about this, as based on some mathematical works that my own feeling is they don't contain much, but at least it puts the problem into a much fancier context. That's one of the questions that is also haunting us. What does it mean to be in the fundamental of ON when n is equal to square root of 2? How can we rely on the tensor product of ON representations when n is not an integer, and so on and so forth? But at least the partition functions are well known. Partition functions, and that's something that Sylvain has been emphasizing to me over the years, and I'm starting to believe it. Partition functions, however, are not very representative of the full CFT. They contain some information, but not everything. And a caricatural example of this is the case of self-avoiding walks, where the partition function is equal to 1, because n is equal to 0, or percolation. It doesn't mean that there are not interesting questions. We know there is a wealth of interesting questions, but somehow the interesting questions, the interesting observables don't appear in the partition function. And that's the way it is, and it's a fact we have to contend with. Now, at this stage, historically, in the 90s and 2000, there was the big excitement about the SLE formalism. As you know, I am myself very cold towards SLE. I think it's beautiful. I think it's also utterly useless for us, meaning, to my knowledge, SLE has not determined anything we didn't know before. And in particular, SLE is also only working, at least in my mediocre understanding, for boundary problems. And all the questions we are really interested in are bulk problems. Now, this is a point where I must make a little remark that's a little bit of a source of confusion, because we are used, in the case of ordinary conformal field theories, we are used to having a deep relationship between boundary and bulk. And roughly, the statement is that if we know all the conformal boundary conditions, we can fold the boundary problems into bulk problems, and we'll also have solved the bulk problem. For many of the problems we have discussed, ON and POTS, we do know quite a bit about the boundary problem. In particular, we know a lot about differential equations satisfied by various crossing probabilities and so on and so forth. Differential equations that can be obtained by SLE or by using degeneracy equations. And yet, we have not been able to use this information at all to rebuild the logarithmic bulk CFT. So the correspondence between bulk and boundary remains open in the case of logarithmic CFTs. One of the reasons is, of course, that there are many infinitely probably conformal boundary conditions in the case of LCFTs, and we don't know what these boundary conditions are. So the only ones we know are not enough to help us in rebuilding the proper bulk CFT. There's been some very interesting work by Matthias Gaberdiel and Ingo Runkel, and many others probably, in the German school, the Hamburg people in particular, on trying to rebuild a full bulk LCFT from boundary LCFT, but this hasn't quite worked. And the examples that are known, like C equals 0, are not satisfactory. They give rise typically to theories with several ground states where we know that the theories we're interested in should have only one ground state. All right, so after partition functions, the big step forward in my mind came from the connection with Liouville and some pioneering work, and here I'm hoping I'm not forgetting anybody, by Aldo, Delfino, and PT, and Raoul, and Santa Clara, and probably Marco also, whom I forgot, I'm sorry. Inspired by remarks of Alyosha Zamolodchikov in some of his papers about the potential relationship with Liouville. So the statement can be formulated in various ways. We don't know everything, and the thing we know has been understood best, I think, in a paper we wrote with Jesper and Yassin, and it's the following. If you take the ON model that I introduced earlier, and if you now define the following quantity, imagine that you have 3 points, R1, R2, and R3, and you calculate the partition function subject to the constraints that loops surrounding point 1 have fugacity N1, arbitrary, loops surrounding point 2 have fugacity N2, and loops surrounding point 3 have fugacity N3, while loops not surrounding any of the points have fugacity N. This defines an object I call Z, N1, N2, N3. By the way, the definition is meaningful on the sphere. That is, if you were to imagine a loop surrounding 1 and 2 and asking what fugacity should you give to that loop, well, on the sphere, this loop is equivalent to a loop surrounding the point R3 by going around the sphere on the other side. So you know that the fugacity you should give it is N3. The problem is completely well defined. This partition function, properly normalized, the issue of normalization is a little bit tricky, but it's been solved, it's understood. This 3-point function involves, well, it behaves like a 3-point function in Liouville at C smaller than 1. That is, first of all, the dependency on R1, R2, R3 is the dependency from conformal field theory. It involves exponents H1, H2, H3, which I'm not going to write down, but they are known function of N1, N2, N3, the fugacities of the loops. And more importantly, the amplitude is given by the equivalent, I'm not going to call it the continuation, the equivalent of the DOZZ formula that has been worked out in the case C smaller than 1, in particular in the original paper of Alyosha's, and then by Volker Schomerus and Kostov Petkova and maybe others. I hope I'm not forgetting anybody. So there is a formula for this 3-point function, complicated formula involving the epsilon function and so on. And it's been checked numerically to incredibly high precision that this formula exactly describes the amplitudes in the geometrical problem. So at the time, this was, I think, very, very exciting. And there was the natural question one could have asked, is Liouville at C smaller than 1 the good theory to describe all these models for C for N or Q real? Now, unfortunately, the answer is no. And that's part of the puzzle that I think we have to contend with. I think it's quite clear what's going on, but it's not the theory, although it may be one theory. That is, it may indeed describe some set of 4-point functions, but there are more than these 4-point functions. In reference to later, one of the key features when you look at Liouville at C smaller than 1, and you calculate the equivalent of the DOZZ formula, is that in Liouville at C smaller than 1, the fields phi21 and the field phi12 are both degenerate. This is a key point in building the 3-point function. And we will see that these facts are not true for the ON or Q-state Potts model. Now, one hint that Liouville is not enough is that there are other 3-point functions in geometrical models which can be perfectly well defined and studied numerically, but are not given by the equivalent of the OZZ. One example is 3-point functions involving Fuso operators, or the watermelon operators. So if you now take 3 points, R1, R2, R3, and demand that a pair of legs connects R1 and R2, while the loop surrounds R3, this 3-point function has also a well-defined form given by CFT. It has an amplitude, which is universal. We have determined the numerical value of its amplitude, but it's not given by the known formula. Nobody knows what the corresponding formula is. Other examples, by the way, would be easy to imagine. For instance, you could take 3 points and then demand that you have a pair of lines connecting each of the points pairwise. This is a 3-point function for which, again, we know the amplitudes numerically, but we don't have yet an analytic formula. And the equivalent of the OZZ does not work, meaning you can take the values of the conformal weights, you can calculate the 3-point function, and it's not what's observed numerically. All right. So now I see I'm running late. I'm coming to the 4-point functions. So this has been the next exciting topic, spurred by a beautiful but not entirely correct work of Marco, Sylvain, and Raoul back a couple of years ago now. And then we jumped on the bandwagon with Jesper, and then now there's a bunch of people working on this. Determining 4-point functions using the bootstrap. So this is part of what we understand. Maybe it's what we understand the best, even though it remains very mysterious. In particular, the relationship with Liouville remains very mysterious. So the first step in determining the 4-point function has been to determine the spectrum. And it was very rewarding to see that the old partition functions we had calculated back in the 90s, in fact, gave us the correct answer. So in fact, the partition functions do give the correct spectrum for the correlation functions. And here's an example for the Potts model. This is the thing that we have all worked on initially, even though it's not the simplest thing. It's correlation functions which are defined geometrically and are deeply related to a 4-point function of the order operator in the Potts model. You imagine taking 4 points and then asking yourself what is the probability that the points belong to either, well, there are various questions to ask, but here I've drawn the relevant ones. Either point 1 and 3 belong to the same cluster and point 2 and 4 to the other cluster, or you can ask whether point 1 and 2 belong to the same cluster and 3 and 4 to the other, or you can ask whether point 1, 2, 3, and 4 belong to the same cluster. And I forgot the diagram, of course, where you can ask whether 1 and 4 belong to one cluster and 2 and 3 belong to the other cluster, right? These questions can be asked. There are more geometrical questions. You could ask, for instance, whether 1, 2, and 3 belong to one cluster and 4 to the other, and so on and so forth. But the point is, when you look at the 4-point function of the order operator in the Potts model, this goes back to old work of Delfino and VT, I think. These diagrams are the ones that matter. So the spectrum is known for this 4-point function. The spectrum in the S channel, meaning when 1 and 2 are brought close together and 3 and 4 are brought too close together. And we wonder what are the operators propagating in this direction. That's this diagram. That's the S channel. The spectrum is known, and it's pretty intricate. It's given in part, well, essentially given by fields which are non-diagonal. There are the form phi rs for the left sector and phi bar r minus s for the right sector. What this notation means is simply that we're having Virasoro fields whose conformal weights are given by the Katz formula. But beware, these fields are non-degenerate. Usually S is not integer. There are no degeneracies. We get the full Verma module. And the point is the labels RS take values in the following diagram. So I'm sorry, in my convention, they should switch S and R. So this is S, I think. I'm always confused. No, this is S and this is R. So the point is that the label S is always an integer. In fact, for the diagrams I've drawn, it happens to be always an even integer, 0, 2, 4, 6, and so on and so forth. But the point is the label R is not an integer, and is pretty much allowed to take any rational value, provided the product RS, which is the spin of the field, is an integer, which means that as S increases, you get more and more rational values of R being allowed. And this is what this diagram represents. So when S is equal to 2, you only allowed R equals 1/2. So 1/2 times 2 is equal to 1. And then S equals 1, S equals 3, R equals 1, R equals 3/2, and so on and so forth. But as S increases, you allowed more and more values. When S is equal to 10, you allowed R equals 1/10, 2/10, and so on and so forth. So what you see, I'm not explaining it very well, but what you see is that the values of R modulo an integer, in the theory, the allowed values of R modulo an integer are in fact dense in the interval 0, 1. Roughly speaking, you get a spectrum that's made of all the rationals. It's not quite true. And what I said is true for the R label, but when you work out HRS, you see that you also get a set of values that dense in the interval 0, 1 modulo an integer. So obviously it's a very complicated theory with an infinity of primaries. All right. So
sorry, a quick question. Are all these primaries seen in the torus partition function?
Yes, they are. They are, and it's fair to say that when we wrote the partition function in the old days, the expression was not particularly elegant. We revisited this with Nick Reed back 2001, and when you look at the new expression, it's much clearer. But yes, they are all in the partition function. And they have a very simple interpretation. The label S has something to do with the number of through lines propagating along the long axis of the torus. And the value R has simply to do with the phases acquired by this line when they go around the short direction, so to speak. And they're all there. With multiplicities, which are fascinating, and we have complicated expressions for these multiplicities. They all involve interesting arithmetic questions, which I'm not going to discuss, but definitely this is fascinating. All right, so this is a mess, and luckily there are ways to put some order in the mess. But before I get to this, it's fair to say that I think we now know the spectrum, thanks to very recent work. We know the spectrum for many of the other questions. For instance, we could, instead of the diagrams I considered, ask the same kind of question, but for the points sitting on the boundaries of the clusters, what I call the L, and we can look at the ON model and the SUN model and so on and so forth. There are many of these spectra, and they all have the same features, essentially. Now, the bootstrap, solving the bootstrap is extremely difficult, of course, if you have such a spectrum, but there is some order that can be put in this mess, in particular with the realization. So there are two ways to think of this problem. One way has to do with what Azad discussed the other day, the interchiral algebra, which is an idea occurring from lattice considerations, but we can reformulate slightly differently by saying that for the CFTs we're interested in, the fields phi21 or phi12, so this depends on the kind of model, on the kind of observables you are looking at, but one of these is always degenerate, meaning it satisfies the differential equation at order 2. Not both, mind you, and that's why we are not having UV, let's see, smaller than 1, but one of them at least is degenerate. So what this means is that even though the spectrum is very complicated, the degeneracy of the field means that we can in fact restrict to conformal weights whose labels belong to this strip here the amplitudes associated with all the other conformal weights, and my diagram would go infinitely high in this direction, but all these other conformal weights can be encapsulated into bigger conformal blocks thanks to the degeneracy of, in that case, phi21. So there are what we call interchiral blocks, and even though things are complicated numerically, they are manageable, and I think we have now very good numerical values for the amplitudes, and therefore for the 4-point functions for n and q generic. Now, it's not the end of the story, because I think there are very strong indications that all amplitudes could be determined analytically. So we are not there yet. We're having these super conformal blocks whose relative amplitudes we determine using the bootstrap. And when I say we, it's a big collaboration in Saclay. But I think we know some of these relative amplitudes between the blocks exactly, and there are indications that we can probably determine them all by algebraic considerations, but we are not quite there yet. This is all for the generic case. So what is non-generic? Well, non-generic is the case where the central charge is given by the old non-unitary values, 1 minus 6 p minus p prime square over pp prime. In this case, the quantum group, underlying quantum group representation becomes non-semi-simple, and it's a mess. There's very complicated logarithmic structure, which has not been studied in general very much. Most of the effort has gone on the C equals 0 case, in particular because we have this nice formulation in terms of SL21 or in terms of OSP22. So there are some things we know. In particular, we know that there are Jordan cells of arbitrary rank in all the non-generic cases. So that's definitely a problem. Not huge, maybe, but the structure is complicated. And you see the complexity of the structure when you do the bootstrap, because you have all sorts of divergences in the amplitudes. And of course, the final correlators must be determined by combining the different divergent terms to make everything finite. And this is the challenge if we want to really understand what happens at q equals 1 and tell mathematicians, yes, this is the 4-point function. We have to solve this problem, and we haven't solved it yet. All right, so the challenges, as you see, I think many of the pieces are there. All we have to do is put everything together. The challenges, immediate challenges, is I think the unknown amplitudes seem to be determined. It seemed to be possible to determine them by lattice considerations. What I mean is that in many cases, we can determine them exactly by studying finite lattices, and we have expressions which we don't know what to do with, rational functions, it seems, in terms of n and q. So that's one of the obvious, I think, challenges we can tackle. Another challenge, which is dear to me and Azat and many others, is that underlying the bootstrap is, of course, a fusion category, which seems interesting, and we don't really control it fully. But you see, when I gave you the 4-point function of the order operators here, and I said that all the fields in the table were contributing to the 4-point function, when you think of this in terms of OPE, what this means is that the OPE of the order operator in the Potts model with itself, the field that was identified as early as late 80s, this OPE formally should expand on all the non-diagonal field phi n Rs, where R and S belong to my big table above with the dense values on the real axis and so on. Now, how to understand this type of OPE, in particular using quantum groups, because we've been used to the fact that OPEs in CFT are in a certain sense dual, Chauvel dual to fusion in some sort of quantum group object, or that there is a simple fusion category. How to understand this in this language is an open question. And if we could do this, of course, this would allow tremendous progress. That's one of the other directions where I think we can make progress. And with this, I conclude my 10-minute talk, which ended up to being a little longer. And thank you.
Okay, thank you, Hubert. Now it's time for questions.
Yes.
So I see there's a question from Jean-Bernard.
That was quick.
No, Jean-Bernard raised his hand, so. But now he lowered it.
No, but he was uploading or raising it?
Oh, he was clapping, okay.
Maybe I have maybe a question. And I learned something that I found important, and I learned from your paper, and that explained me these days, is that indeed there can be logarithmic structure that appear in the continuum limit and are not visible on the lattice. And
that's true. Yes.
And the bootstrap I think this is a nice, let's say, success of the bootstrap, that it could find this logarithmic structure,
yes.
even implementing logarithmic structure in the bootstrap approach, but also by doing some limiting procedure from a standard 0-0 module.
Yes.
So
yeah.
this
The amplitudes are beautiful. They're very, yes, they know everything about the logarithmic structure. Absolutely, yes. That's a good point.
And also, like I want to stress, if I'm not wrong, the fact that we find this Liouville C-1 structural constant, which are not all the constant, but it's still a bootstrap. It's still a bootstrap result.
I suppose there are correlation functions which we haven't studied, but must be fully determined by Liouville. If I were to ask myself, if I were to consider a 4-point function now where I suppose I give myself 4 points and I ask what is the probability that, I mean, what's the partition function with loops surrounding point 1 getting fugacity n1 and so forth. I suppose this 4-point function would be described fully by Liouville. Or is it? I don't know. But
Liouville, you mean a structure constant to Liouville, not this theory with continuum spectrum.
Well, we know that the 3-point functions are described by Liouville at C smaller than 1 for these things. So if I were to calculate the 4-point function as a function of n1, n2, n3, and 4, would it be the Liouville 4-point function?
But how is it? So in this case, the geometric arguments that you gave on the sphere, you may need more than 4 fugacities, right?
Yes. So absolutely. So this is a good point. I think that's what Jesper is about to say as well. But it's that in this case we have to solve the ambiguities for loops surrounding pairs of points and so on and so forth. There are more topologies to consider. But I think, in fact, we probably wrote some speculation about this in our paper about minimal models. There must be a good definition which would correspond to Liouville. Was it what you were about to say, Jesper?
Exactly. I mean, when you have n points, you can surround each point by loops in 2 to the n ways, but then you have to divide by 2 because of the fact that you're on the sphere. So you have 2 to the n minus 1, and then you subtract 1 because you already have the bulk loop that sets the CFT. So there will be, I guess, seven special weights here.
In our paper about minimal models, we kind of, okay, I forgot a bit about it now, but I think we interpreted geometrically the 4-point function of order operators in minimal models, and then we extended this definition away from the special values of minimal models and kind of speculated that this was related with Liouville. I forgot a bit, but it's an interesting question, what to do with these structural constants. And I'm sure there's a formula for all the structural constants anyway.
But for this 4-point function, shouldn't we be able to do something similar where we just replace these n3 and n4, for example, by 1 using the fusion? Similar to what we did.
I think that's
sum over all the ones that are non-zero.
Yeah, it's what we speculated in our paper, but I forgot if it's only a speculation or whether we proved it. I kind of forgot now. But anyway, it would be nice to see it coming out of the brute force calculation of the 4-point function in that case and see the amplitudes coming out. But
right, because in the RSS case, it all worked out very nicely this way.
Absolutely, yes. Yeah. So it's something I didn't really mention, but there are all these things one can think of about these generalized minimal models, the RSOS models, and what they have to do with this picture is, again, something we know the answer to mostly, but it's still a little bit confusing.
You have maybe a comment on the chat. Maybe there is a Benoitian comment on the chat.
Yes, that's what I mean. Hi there. Yeah, I would like to mention a paper with Yacine that is not being cited very much. But
that's absolutely true. The paper with Benoit and Yacine, yes.
So, for instance, you mentioned these Johnson cells that have been discovered recently for generic value of n. We already mentioned them 6 years ago.
Actually,
or that non-diagonal spectrum, yeah. But you know, it was a very nice presentation.
So in the paper, you mentioned that the theory is generically logarithmic.
Yes, yes.
I think I had missed that actually. How did you know it?
From numerics.
Numerics of the 4-point function?
No, for analysis of the transfer matrix and looking at degeneracies in the spectrum. Or if you want, we conjecture it, if you prefer that, rather say we know it, we're not doing mathematics.
It's precisely one of these situations where, like Raoul was pointing out, it's not logarithmic on the lattice. So it's something that occurs only in the continuum limit. What happens is that for Q generic, I mean for C generic, there are these fields which conformal weight HRS, non-diagonal.
Yeah.
And what happened at level RS below is that there is a Jordan cell of rank 2 that appears in the continuum limit, but again, only in the continuum limit. That's why it's something you have to see either by using bootstrap arguments.
I agree. But if you want, we guessed it, then it's written on the paper. You can look at equation 428.
Okay. Okay.
You see the Jordan block with exactly this field.
I see. Okay. Well, very good. Sorry, I didn't mention it. Yeah, I keep forgetting this paper because it never got published, I think.
Yes, it's only on the archive.
Yeah. Whenever I go over, or whenever I go over references, it drops between the cracks because of that. Yes, and there are also some nice calculations of 4-point functions in this paper. Absolutely. Yeah. Sorry, I forgot.
So I have maybe a general question. I mean, all these geometrical models in the continuum, they're described by something that we are calling a non-unitary CFT. And I'm not actually sure what that means. I don't know what the non-unitary CFT is because I don't know how to define the OPE. I don't know how to define even the state operator correspondence. Even there might be some issues. So my general question is if you have some comments to make regarding this point and how maybe the original lattice formulation for some of these models can give us some clues on how to define these theories properly in the continuum.
You mean how to define a non-unitary CFT? Yeah, yes. I think so. There are various levels of non-unitarity, of course, and the simplest non-unitary theories are the non-unitary minimal model, like Yang-Lee theory, where non-unitarity manifests itself simply in some negative signs, like the central charge. The kind of non-unitarity we are dealing with is systematically, I mean, I would almost take it as a definition, but it's systematically associated with the existence of Jordan cells of rank 2 or higher for L0, and the fact that the Virasoro invariant metric Ln dagger equals L minus n is not positive definite. This does not, however, prevent us from defining Braz and Ketch and defining the state operator correspondence. I don't think so.
Well, do you even have a Hilbert space? I mean, you have
we have a space which I would not call Hilbert maybe, but yes, we have a space. So usually I fall back in these cases to the models which are the best defined, which are the models based on superalgebras like SL21, for instance. So this is closely related with percolation, and the best lattice realization is tensor product of the fundamental representation of SL21 and its conjugate. So this is a space where we're having a well-defined SL21 invariant metric, and it's not positive definite. But other than this, we do have a space, we do have a scalar product, and
For instance, is the space complete? Can you introduce bases?
Absolutely.
All basic questions, right? To prove the existence of the OPE. Usually this is done by the Hilbert space formalism, right?
Well,
Here
you don't
have
really,
that, so.
you don't really require unitarity. Oh, excuse me, I have a phone call. Sorry. Hello? Oui? D'accord, oui. C'est annulé. D'accord, très bien. Je lui fais savoir. Oui, oui, je lui fais savoir. OK, merci beaucoup. D'accord. J'espère qu'il est pas parti. Merci beaucoup. Au revoir. Maxime, tu es là? Il n'y a pas
It's all being recorded.
Yeah, this is being recorded.
Sorry. School called, class cancelled. Sorry, where were we at? Yes, we don't really require positivity of the scalar product to define the theory.
I agree if you just give me a bunch of correlation functions satisfying crossing. I mean, you don't necessarily care. But if you want to talk about the theory, this class of theories more generally,
why would you
know how to define the DOP? Because I need completeness. I need a basis. I need to. I need that basis decompositions converge, for instance. And I know how to prove that in a Hilbert space, but if I don't have that, I'm not even sure.
Yeah, it seems to work.
So my question is, here in this case, you also have the lattice formulation, so perhaps there things are under better control, and they can give you some guidance on how to define the theory in this sense.
Yeah, I mean, certainly at the level of the lattice, there is no problem in defining. We can always use other scalar products that are positive definite in order to ascertain questions such as, is a state of zero norm square really equal to zero, for instance, or things like this. But if you are really worried about the CFT, then I would take another angle and say this is a kind of question we have studied a little bit in papers with Volker Schomerus in particular, using the other angle of attack, which is the mini superspace approach, functional analysis on something like GL11 or SL21, and you can see in that case that all the theorems, Peter-Weil decomposition and all that work in the unitary case extend to these cases as well. There is not really a difficulty about completeness or convergence of the OPEs or anything that I know of in these models. But yes, I mean, the question remains, we are, it's always a little bit risky when you give up unitarity. But yes, I mean, the lattice, I mean, it has been the philosophy that we have used over the years, that the lattice models do give us an organizing principle that we wouldn't otherwise have. To put things mildly, whenever you give up unitarity, for instance, it's known that the Virasoro algebra has a representation theory which becomes wild. There are absolutely no classification theorems for the kind of representation we could get. So any kind of top-down approach is bound to fail. But if you start from the lattice model, you get a very clear idea of the kind of modules you're going to get in the continuum limit, and this definitely helps us conjecture a bunch of results. Yes.
Well, as a bootstrapper, for instance, one of the reasons why the bootstrap works so well is because we have exponentially fast convergence in the OPE. Yeah.
You have that also in this model. I mean,
yes, in these models you have that, but this is by observation, right? I mean,
yeah, it's by luck, I suppose. So, are you saying that
the question is whether it's more than luck, or if we know how to, can we come up with some criterion that would at least give us some class of theories where this property would be true?
Let's go back to the unitary case then. How do you know, for instance, that the bootstrap approach would converge exponentially? Is this a theorem that uses unitarity?
Yeah, it uses positivity indeed. It's a paper also by Slava, Papadopoulou.
I see, I see. Okay. Yes.
So it's convergence of the OPE plus unitarity, then you can use basically the Tauberian theorem to place some bounds and show that the OPE converges exponentially fast.
So that's an interesting question. I wonder what the arguments, what the ingredients are, and what kind of generalization we could think of to see what happens in the non-unitary case. Yeah, that's...
yeah, in this case, positivity is really crucial.
Positivity of the scalar product, I mean the inner product.
Yeah, that OP coefficients squared are positive.
Yeah. It's fair to say, right, Sylvain, that in our case they're not. So yeah, it's a very interesting point. Yes, I have absolutely no idea. Yes, I mean, again, in the lattice, for the lattice model, it's unitarity essentially plays no role in the structure of the theory, but then there's the question of taking the scaling limit and exchanging limits. So that's very tricky. It's a very good point. Yes, I don't know what to say.
So I would like to take the opportunity of mentioning another point. So here you have shown us this quite staggering perspective around these loop models. But in some sense, they are only the simplest possible models that you can think of. So on the lattice, you have loops, and the underlying algebraic description is provided by temporally, or it's a fine extension. And from the point of view of quantum Schur-Weyl duality, on the other side, you have UQSL2, while in the continuum limit, you have the Virasoro algebra, of course, with these interchiral conformal blocks, but in some sense, it's just Virasoro. But if you now replace, for example, SL2 by SL3, then there are perspectives for doing similar things. So instead of loop models, you will get bifurcating cubic graphs known as Cooper-Berg spiders. And you will get extended CFTs on the other side. And for all of this, you could go around and ask basically the same question, the same set of questions. And this has, to some extent, people have started looking a little bit at this. There was some work by Yacine Benoit and Thomas Dupic, I think. And with Azad and their thesis student Augustin Lafay, we are trying also to look at these Cooper-Berg spiders. So there's certainly some room for extending this panorama even further.
Yeah.
I have a question as well. So thank you, Hubert, for a very nice talk.
Hello, Alexei.
Hi. So you mentioned this interchiral algebra with two fields, phi 0.5 and phi 1/2 0, one of which you said was degenerate. Does that mean that you have some knowledge of the singular vectors? And can this knowledge be used to derive differential equations for 4-point functions of this field?
So what I said is that phi 2,1 or phi 1,2 are degenerate, right?
Okay, yeah.
This is the statement. And yeah, I mean, the differential equation is telling us, for instance, that the fusion of phi 2,1 with phi RS, where R and S are arbitrary, is phi R plus 1S plus phi R minus 1S and things like this. But that's it. I mean, okay, there are other things I could say. One of the questions you could ask, for instance, is how about the 4-point function of phi 2,1? Right? So that one is well known in these models. It is indeed given by the solution of the level 2 differential equation. But I think we use fully the information about the degeneracy when we build the super interchiral, sorry, the interchiral conformal blocks. That's about it. I wouldn't know what else to do. But one related question has always been whether there are other equations associated with the interchiral algebra. We suspect there are, but we don't know any more on this for the moment. Is this the question you were asking, Alexi, or
Yes,
was I?
Yes, I think that's correct. So I understand. Also, so do you expect this interchiral algebra exists for all values of the central charge?
It seems to, yes, definitely. We have a strong evidence for, I mean, yeah, we definitely know it does. And in fact, it even exists for minimal models, which is something that we have never really written down explicitly. But when you look at minimal models and you look at the partition function, you know that the partition functions are built up with blocks of sum of characters that you combine with various coefficients, and the presence of these blocks has something to do with the underlying interchiral algebra. So this is an idea that's not been pushed too far, but I think it could be profitable. So if you wish, we have models for which phi21 and phi12 are degenerate. We have models for which only one of them is degenerate, and I don't know if there are models for which none of them is degenerate. I mean, natural lattice models for which it would be a complete jungle with no degeneracy at all. This is another interesting question that we were wondering about. Yeah, I don't know about this.
Okay, thank you.
You have a geometrical interpretation of what non-unitarity means?
A geometrical interpretation of what non-unitary means. So I will resist the temptation to invoke non-locality. I really am convinced that non-unitarity has nothing to do with non-locality. But apart from this, no, no, I mean, I think any geometrical model seems to be naturally non-unitary, except for some very specific cases. But no, I mean, it's a daunting question. I don't really know. It would be nice to have a more geometrical interpretation of what.
Sorry, why are you saying that you don't think it has anything to do with the locality or non-locality?
Because there are models which are completely local and are described by logarithmic CFTs. For instance, the SL21 spin chain or the GL11 spin chain, a completely local model defined in terms of graded degrees of freedom, maybe, but it has a local Hamiltonian and so on and so forth, and yet it's non-unitary, and yet it's logarithmic. So this is why I think non-locality is a red herring. And anyway, we know that non-locality usually works against conformal invariance. But on the other hand, I'm not providing a very good answer. I'm aware of this. I would like to have a nice geometrical. I would reformulate your question by saying it would be nice to have a geometrical formulation of L0 Jordan cell. What exactly does it mean? Having an L0 Jordan cell means that if you do a scale transformation, your field is not only multiplied by a rescaling factor, but also acquires another component. That's the nature of the Jordan cell. And if we could understand this geometrically, I think it would be very helpful. But I've never really quite succeeded in doing that.
Couldn't we maybe try to answer this question in the context of the Ising model? Because that model has local and non-local observables. It also has unitary and non-unitary 4-point functions.
Yes. Yeah, here it looks like the answer is the non-locality, because you would say, well, any correlator that's local in terms of spins is described by the minimal theory. And the other correlators, like what is the probability that 2 points belong to the same cluster, is described by some non-local quantity. But again, I resist non-locality because if you try to build a field theory that's non-local, usually you break conformal invariance, and it's important to remember that the theories we are dealing with are conformal invariant. They may be logarithmic CFTs, but they are conformal invariant. So that's why I'm always uncomfortable with involving non-locality. We can involve mutual non-locality, and that's fair. So the minimal model is described by a set of observables, which is not mutually local with the set of cluster observables, for instance. So it's normal that we're having two CFTs. But anyway, this is mostly semantics. I don't know what else to say.
So, Hubert, can you comment on, there was also a nice scenario that comes out from the bootstrap solution, no? You say that, like, it seems that associated to the affine temporally algebra, there are like a series of an infinite, probably an infinite series of family of bootstrap solution. For example, ours was the most simple, the first of this series, and then the POTS model is the next one. But you have someone said in your paper that you can think this as like some you know, like the first two members of a family of
Yes.
a series of solutions.
Yeah, it had to
maybe are like the, you know, the total, what the Virasoro symmetry can do, that is probably strictly connected to the temporary algebra.
Yeah, I am not. I think the idea came from our paper on the minimal models, where we speculated, or more or less proved in our paper, that the initial solution you had with Marco and Sylvain was describing a geometrical model which was not quite the POTS model, but a model where non-contractible clusters in the sphere with 4 punctures, where non-contractible clusters were given some rather complicated weight that was inherited from the geometrical formulation of minimal models. So then we speculated that one could imagine other categories of models where these non-contractible clusters would be given yet other sorts of Boltzmann weights. And definitely for each of these choices of weights, there should be associated 4-point functions for which we would know the spectrum and for which there would be a solution to the bootstrap, yes. Now, I don't think these models would have the interchiral algebra symmetry, but maybe I'm wrong. I forgot a little bit about this, but it was the general idea. Again, it goes back to the main question, which is what was your solution describing and how does it compare with the POTS model? And since there are at least 2 solutions, it's tempting to think there are many more, depending on how you weigh these non-contractible clusters. So it's very mysterious from the point of view of HCFT or CFT that there would be all these solutions to the bootstrap, but this seems to be the case. I don't know what it means. There might be there might be classifying algebras. But again, remember, in your solution, in the end, your 3-point functions were 3-point functions of UV, let's see, smaller than 1, finally. So you are looking at a model where phi21 and phi12 are degenerate. The true POTS model is one where phi21 only is degenerate. It's not clear from this point of view that there are many other models, except one where none would be degenerate. Now, if none is degenerate, then maybe there's a continuous solution, there's a continuous family of solutions to the bootstrap. It could well be, I have no idea.
Robert, I have a question. So I remember that there are settings where the CUTS labels can be not only rational, but irrational, right? Is it always associated with a boundary somehow? Or I mean, what's the general sort of feeling?
Irrational labels in the CATS formula?
Yes.
Like what?
I think it appeared in our paper on the edge states. Maybe I'm already forgetting things. So instead of having, there's no interpretation for these things as number of lines going through the system. But
it's I forgot this, but it's in the bulk. I'm not aware of this.
No, it's not about the bulk. I mean, I think it's definitely appears in the context of this boundary.
I see.
Sorry, shouldn't we be able to do that because our CATS labels depend also on the twist of the twisted boundary conditions? So at least formally, if we set this twist to something irrational, then we would just get at least that CATS label. Yeah.
Yeah, it is true. It is true. I'm not sure.
I'm not sure if it corresponds to anything physical though, but at least formally with our construction, we can get any CATS label we want for at least one of them.
Yeah, I mean the fact that the CATS labels are rational does not seem to play a role. I'm thinking it doesn't play a role in the calculation of the conformal blocks, for instance. I don't think it does. Yeah, so, but I think, Ilya, the question you're raising is interesting, also in the sense of classifying boundary conditions, conformal boundary conditions for logarithmic.
That's what you mentioned. Yeah,
I think it's a very, very, very important question. We are used in minimal theories to have a correspondence between every primary field in the bulk theory and the conformal boundary condition. And here we're having this infinity of primary fields in the bulk, and there has to be a lot of conformal boundary conditions that we don't know about. And maybe they have some interesting physical meaning. In particular, in the spin quantum hole or percolation. Yeah, I don't know. It would be nice to understand this better.
Now the question, when the models are integrable, does it tell you something about the OPE or convergence? When many of these models are integrable.
It's a little bit tricky. It's a little bit tricky to say the models are integrable because, of course, all these models are related with integrable models. But if I took, for instance, the SL21 spin chain, it is not integrable in the Yang-Baxter sense. The Hamiltonian does not belong . I mean, the way it works is we use integrable models to calculate the eigenvalues, but the spin chain itself is not really an integrable model in the quantum inverse scattering sense. So there's a little bit of a subtlety here. But apart from this, yeah, it's a good suggestion. In fact, this is something we have tried in other models, in genuinely integrable super spin chains, for instance, the SL21 spin chain. And one of the things we were trying to see was whether we could understand the Jordan cells directly in the formalism of the quantum inverse scattering approach, which is an interesting question, but it never gave rise to much. So my answer is really moot. I just don't know. It should be possible, definitely. It should be possible. For instance, one could calculate scalar products of states and see whether some states prove analytically that some states have norm square 0 in the continuum limit by using these formulas of Slavnov and company. But no, so far the integrable structures has not been used very much. But I want to emphasize again, it's an important point that these models we are looking at are not really, strictly speaking, integrable. They are related with integrable models. You can calculate, for instance, Potts model for Q generic, you can calculate all the eigenvalues of the transfer matrix using the mapping onto the 6-vertex model, which is integrable and so on and so forth. But I don't really know directly an integrable formulation of the Q-state Potts model for Q generic that would allow me to use the quantum inverse scattering formalism to calculate all the eigenvalues and their degeneracies using the beta answers. I don't quite know how to do that. It's an interesting question. Are you in Santa Barbara, Kay?
Pretending I'm an also.
Pretending, yeah, that's what I suspected, yeah. Okay, maybe this is it. I'm getting a little tired and it's 11:30. Did I do enough of a job? Okay,
It was
good.
a nice extension of the promised 10-minute presentation.
Yeah, thank you. All right. Well, thank you everybody for your time. Sorry, I forgot some references. I probably forgot.
Thanks a lot.
Apologies to everybody. Okay.
Thank you.
Thank you. Talk to you soon all. Bye-bye.
Thank you, Beth.
Bye.
Yep.